Good evening, everybody. Welcome to day one on week 3 of the semester. So to recap what we talked about last week on Thursday, the last thing that we mentioned as part of chapter 1, which we will be finishing up today and moving on to chapter 2, is applications of specific heat. We learned that when it comes to specific heat, this is a value that when we are comparing different substances, depending on the value of specific heat, we can determine which substance will heat up faster. Remember, the substance with the lowest specific heat, in this case, copper, will be the substance that heats up faster. Because when it comes to specific heat, remember that this is going to be specifically the amount of heat that is required to heat up 1 gram of a substance by 1 degree Celsius. So, moving on to the next topic in chapter 1, which is section 1.5, we are talking about measuring matter. When it comes to measuring matter, it is important that we understand the difference between accuracy and precision, because sometimes those terms in everyday language, people use them interchangeably, but they are actually very different. So going into the definition of accuracy versus precision, understand that accuracy in chemistry refers on how close a measurement is to the true value, okay? So when it comes to accuracy, understand that we're going to have like a known density. We're going to have a known value in our measurements. We're going to see how accurate it is because we're going to compare it to the known value. So in order to increase the accuracy, understand that at times in the laboratory, we need to calibrate an instrument, okay, that we may use for taking a measurement. So for example, when it comes to balances, they tend to be calibrated to make sure that they are accurate. When it comes to precision in chemistry, as you can see, by definition, it's a term that is attached to the reproducibility of a measurement, meaning if you have different measurements, how close they are to one another. So if we utilize specifically the example that we have on the right side of the slide, using a dart game to exemplify what is accuracy versus precision, we can see that because in darts, the main goal is to hit the bullseye. If you throw darts, as you can see here, and they all hit the bullseye and they are close to one another, that means that this measurement is going to be having good precision and good accuracy. Precision because the darts are close to one another, accuracy because you hit the target. What happens in a situation in which your darts or your data for that matter, the numbers in your data are close to one another, but far away from the target? Then understand that that means specifically that they can be precise, but they have poor accuracy because, as you can see, that is far away from the target. Lastly, what happens if we have darts that specifically are scattered all over our board? Well, that can happen also with data. And when that happens, we describe that data as having poor precision or accuracy because, first of all, the data, or in this case, the darts, are not close to one another, and they have poor accuracy because none of them are hitting the bullseye. Any questions when it comes to the difference of accuracy versus precision? Then let's move on to section 1.5, in which we're going to talk about measuring matter, but specifically, we are going to focus on units and dosing, okay? So many of the students that come to Chemistry 112 are going to be going into nursing programs, okay? And there are a number of measurements and equalities that are very important in this field. Give me one moment. One of those equalities that is very important is determining specifically what is the weight of that patient, or in veterinary medicine, animals, so on and so forth. So it is very important to know how to convert between pounds and kilograms, because in the laboratory, whenever you have dosing of a particular medicine, typically is done by the weight in kilograms. So here in the bottom, I have an example of taking kilograms to pounds, but it's important to do also pounds to kilogram transitions. So for example, in the problem below, it says, what is the weight in pounds of an animal that weighs 150 kilograms, okay? So in here, we can see that the important equality that we need is this one. 2.2 pounds equals 1 kilogram. So when it comes to this, which is an English unit, so US unit to metric system conversion, we're going to write in the amount given, 150 kilograms. And then using dimensional analysis, in the bottom of our fraction, we're going to write 1 kilogram. On the top, we're going to write 2.2 pounds. So to do this conversion, we're going to multiply 150 times 2.2, and we're going to divide it by 1. Let's put in the chat, what is the result from this multiplication? If I take 150 times 2.2. Thank you, Isaiah. 330. Now, remember, whenever we're doing conversion, we need to take into account what are the sig figs given. How many sig figs in 150 kilograms? Let's put it in the chat. How many sig figs in 150 kilograms? I see some 3s and I see some 2s. The correct answer is 2 sig figs. That 0 is not that it's unimportant, it's just a placeholder. So if I give you a measurement with 2 sig figs, this needs to have 2 sig figs. Does the value 330 have 2 sig figs? Yes or no? Does the value 330 has 2 sig figs? Excellent. Yes, it does. So since it has 2 sig figs, we're done. There's nothing that needs to be done. But understand that this conversion between kilograms and pounds, pounds and kilograms is very important in dosing. Now, for those students that are in kinesiology or nursing, understand that the examples that I'm going to give you in terms of how to figure out how much medicine to give a patient are going to be very specific. I'm going to only give you guys 2 types of problems, okay? This is the first type of problem that we're going to be dealing with. It reads, a doctor's orders prescribed a dosage of 0.150 milligrams of Synthroid. Synthroid is your medicine, which I'm just going to label med. Next, it says, if tablets in stock contain 75 mcg, mcg is the same thing as saying micrograms of Synthroid, which is my medicine, how many tablets are required to provide the prescribed medication? Understand that in clinical problems, it is one of the few instances in which I tell you guys, hey, I want that answer in this specific number of significant figures. So you can see here that at the end of the day, I want you guys to express your final answer in one significant figure. So how do we deal a problem with this? So first, you need to identify that this problem in terms of the words only gives you two pieces of information. Piece of information number one, the doctor's orders. That is 0.150 milligrams. Piece of information number two. It tells you that you have 75 micrograms of the medication per one tablet. This specifically is what we called a clinical factor. And a clinical factor, you guys, is basically what we have of the med in hand, which it could be, hey, this medicine is a suspension. So every 5 milliliters is particularly this many milligrams of the medication. So medication can come in tablets, in capsules, they can come in liquid form. And here we're dealing with a tablet. So again, when the information that tells you what is the amount of medicine that you have in a liquid, in a tablet, in a capsule, that is known as the clinical factor. So when you're giving a problem like this, first thing that you need to do is, let me look at the units that I have. You can see here that the units that were given for the prescription were in milligrams. The units given for my clinical factor, they're in micrograms, so they do not match. This is very crucial when you are trying to determine the dosing of a patient, because specifically, this is where the overdosing or underdosing actually occurs, okay? So the first thing that you need to make sure, and you can pick, you can make your clinical factor match the doctor's orders, or you can make the doctor's orders match the clinical factor. I prefer to do a doctor's orders match my clinical factor. So in order for them to match, I have to tell myself, the first thing I'm going to do is take 0.150 milligrams, and I need to convert that into micrograms. So when I'm going from milligrams to micrograms, 0.150 milligrams, how many micrograms is that? Let's put it in the chat. Milligrams to micro. Thank you, Kiyomi. Let me do the number line to remind students on how to use this for the exam. So I have 0.150 milligrams, and I need to find out what is that in micrograms. Milli is here. Micro is here. So I need to move that decimal place 1 time, 2 times, 3 times from left to right. So I move this 1, 2, 3. That's where I get the 150 decimal place micrograms, okay? So taking that into account, I know that basically what I have to give my patients is 150 micrograms of the medication. So now that I did that, I'm going to write first my doctor's orders. Then I'm going to use my clinical factor as a conversion. So, because I have micrograms in the doctor's orders, then I'm going to use the amount per tablet as my conversion factor. In other words, I can express this as 1 tablet equals 75 micrograms. So 75 micrograms are in the bottom, 1 tablet is on the top. The micrograms cancel each other. So how many tablets do I have to give this patient based on the doctor's orders? Let's put it in the chat. 150 divided by 75. Excellent work. 2 tablets is what I need to give this patient in order to follow the doctor's orders. Let's practice. Do the following. A patient is prescribed 1.25 grams of amoxicillin, which is available in 250 milligram tablets. And you need to figure out how many tablets we need to give this patient. You need to express this in one significant figure. I'm going to give you guys 2 minutes for this. Let's go through the solution of this problem. So as you can see, instead of a doctor order, here we have a prescription, basically the same thing. So we write, what is my prescription? 1.25 grams of the medicine, which as you can see is amoxicillin. Then my clinical factor says that there are 250 milligrams of the med per tablet. So when it comes to the solution of this, first we write the prescription, or let me go step by step. We look at the units of the med versus the unit that I have in my clinical factor. Let's put it in the chat. Do they match? Excellent. They do not match. So taking that into account, I need to make them match. As I mentioned, I like to always match my prescription or my doctor's orders to my clinical factor. So taking that into account, I'm going to say 1.25 grams, I need to change into milligrams. Let's put it in the chat. 1.25, what is that in milligrams? Thank you, Vanessa. 1,250 milligrams is what we need to give this patient. So now I'm ready to write, again, my prescription or my doctor's orders. 1,250 milligrams. That's my prescription. Then I'm going to use my clinical factor as a conversion factor. 250 milligrams of the medication per 1 tablet. I'm going to cancel milligrams with milligrams. How many tablets do I need to give this patient? Great job, 5 tablets. Any questions on this type of clinical factor problem? Then let's move on to the next type of clinical problem that you guys need to be comfortable with. That is, what if I have a prescription or a doctor's orders, but it's going to be dependent on the body weight of my patient? So this is the example. It says, give Fortas at 50 milligrams per kilogram to a child who weighs 56 pounds. Fortas is available as an oral suspension, which means that 100 milligrams of the medication is what you get for every milliliter you give. We need to determine how many milliliters we need to give to this child. So let's write the information. So in these problems, we have 3 pieces of information. We have prescription or doctor's orders, which in this case, it determines that we need to dose this patient at 150 milligrams of the med per 1 kilogram of the body weight of this patient. In this case, it is a child. We have the weight of the patient. In this case, that is 56 pounds. Lastly, we have our clinical factor. And our clinical factor says that every 100 milligrams of the med are going to be given if I give 1 milliliter to my patient. So in a problem in which you have these 3 pieces of information, this is how you solve it. First, you write the weight of the patient. The first conversion is going to be using the 1 kilogram equals 2.20 pounds conversion. So you're going to say in the bottom, 2.20 pounds, and on the top, 1 kilogram. Next, we need to make sure that my prescription unit and my clinical factor unit match. Do they match? Yes or no? Let's put it in the chat. Great. So since they match, we can move to the next stage, which is now I'm going to use the prescription, okay, as a conversion factor to figure out how much medicine do I need to give this patient. So based on dimensional analysis, because we cancel units diagonally, I'm going to have 1 kilogram in the bottom, and on the top, I'm going to have 50 decimal place milligrams of the med. Lastly, I'm going to use my clinical factor. And my clinical factor is going to tell me how much medication I'm going to give them. Okay, so that being said, When it comes to this, we are going to use our clinical factor, in which we're going to say 100 milligrams of the med correspond to 1 milliliter. When it comes to the cancellation of units, as you can see, pounds with pounds, kilograms with kilograms, milligrams of med with milligrams of med. So overall, when I take 56 and I multiply it times 50 times 1 times 1, and I divide it by 2.20 times 100, okay? And I need to answer this in two significant figures. What's my final answer? Thank you, Maria. 13 milliliters is what we need to give. Any questions on this type of problem? There's a question in the chat. On the test, if we don't show our work, we'll be marked off. The thing is that the way that I write the exams, you guys are going to be submitting just the final answer. So you will not be showing me the work that you do. So be careful with this type of question, because you will be writing or entering just the number 13. So there's a question in the chat, how did we get 13? So in order to get 13, what I enter in my calculator was 56 times 1 times 50 times 1. And I divided that result by the result of 2.20 times 1 times 100. That's how we got 13. That's how I enter it in the calculator. Any other questions? Let's practice. I will give you guys 2 minutes. The problem reads, the doctor orders Lanoxin at 20.0 micrograms per kilogram. The stock supply is Lanoxin 0.125 milligrams per milliliters. Your patient weighs 150 pounds. We need to figure out how many milliliters would you have to administer for this patient. So I'll give you guys 2 minutes. One more minute. Okay, let's get started looking at the information. So here we have the doctor's orders, which the doctor's orders say that we are going to give this patient 20.0 micrograms. So instead of MC, I'm just going to write the U per 1 kilogram. We also have the stock supply, which we know this as our clinical factor. Third piece of information, the weight of the patient, okay? So what is the first thing we're going to write when we're doing this problem? First thing in our equation in order to solve it. Let's put it in the chat. Great, the weight. So we're gonna do 150 pounds. We're gonna convert that to kilo. So we're going to say we divide by 2.20 pounds. On top we say 1 kilogram. Now, before we move forward, I want you guys to pay attention to what I've mentioned before. My clinical factor and my doctor's orders, do they match in terms of units? Thank you, Katie, they don't. So what do we need to do? Make sure that my doctor's orders match my clinical factor. So in this case, I'm going to take 20.0 micrograms and I'm going to turn that into milligrams. Okay, so when I do that, how do I make milligrams from micro? What is the result if I make that change? So what is 20 micrograms in milli? You can use the number line. Thank you, Vanessa. Excellent. 3 decimal places we're going to move. Thank you, Kiyomi, for putting the answer. So this is going to be 0.020 mg. Now we are ready to put in the doctor's orders, which we have to say, okay, per kilogram, I need to give this patient 0.020 milligrams. Next, we use our clinical factor as a equality, as a conversion factor. So as you can see here, we're going to say 0.125 mg, which is what I have of the medication, per 1 milliliter is how I get to my answer. So I'm going to cancel the pounds with the pounds, the kilograms with the kilograms, the milligrams with the milligrams. So overall, I'm going to take 150 times 0.020 times 1, and I'm going to divide that times 2.20 times 0.125. So what did you guys get? Excellent. That's what I got also when we rounded to 3 sig figs. 10.9 milliliters. For those students that need to know, how do I get that by entering in the calculator? 150 times 1 times 0.020 times 1. All of that, I'm going to divide the result of that by 2.20 times 1 times 0.125. Great question, Morea. So when it comes to this, because I told you to express your answer in 3 significant figures, and let me do the whole calculator display. 150 por 0.02 dividido entre 2.20 por 0.95. So the calculator display is 10.90909091. So you have to go based on your calculator display. That's why it's 10.9, not 11. So 11.0 will be incorrect because your calculator display is showing something else. Any questions on doing clinical problems? Then let's move on to the next topic, which is section 1.6, is how matter changes, which this is what you guys are doing in lab this week. It is important to note that when it comes to matter, matter comes in different states. Matter can be a solid, a liquid, or a gas. In the following table, you have the different states of matter: solid, liquid, gas. There is a fourth one, which is called plasma, but we don't have a lot of examples of it. So understand that that fourth one, we're not gonna discuss in this class. So when it comes to the characteristics of solid, liquids, and gases, for exam 1, you need to know them in terms of shape, volume, arrangement of particles, interactions between particles, movement of these particles. And we even have different examples here. So it is important that you have this table for exam 1, which exam 1 is next week, okay? So you need to understand what are the descriptions of those characteristics for solid, liquids, or gases. Now, knowing that matter comes in those different states, we need to understand that matter is going to have characteristics that can be observed. And that's what we know in chemistry as a property. So as you can see, by definition, a property is a characteristic of a substance that can be observed. Now, we have two types of properties. We have physical properties, and you can see them on the left, and you can have chemical properties, which is what we have on the right. Physical properties, they can be observed without changing the identity of the substance. So some examples of physical properties include luster, which means if something is shiny or dull. Melting points or boiling point, which is the temperature at which you have matter going from solid to liquid in the case of melting, or in the case of boiling point, when things are going from liquid into gas. Malleability, if we can mold it. Ductility, if we can make it into wires. If something is a solid, it's a liquid, it's a gas. Density is a physical property. Solubility is a physical property, and also odor. Now, we can also have chemical properties, and those chemical properties can only be observed when you change the identity of the substance that you start with. So what that means is that chemical properties are going to at times describe the changes in substances because a chemical reaction happened. So as you can see, flammability. For example, if my substance caught in a flame. So this is something that you guys will be seeing in the videos for this week's lab. Combustibility, if my substance undergoes a specific reaction, which is called combustion. If my substance is specifically toxic, meaning that let's say that we are comparing toxicity in the human body or in animal models, you'll be able at what dosage that molecule be interacting with some other molecule in the body and is going to create this toxicity. pH, which is something that we're going to talk about later in the semester. This tells you the ability of a substance to be giving away hydrogens. Reactivity with water, air, acids, the ability to form rust, because rust is a specific compound. That is just basically when iron mixes with oxygen, or for that matter, if you have a compound that makes a new substance that has oxygen in its chemical formula. All of those are examples of chemical properties. So understand that here I have a series of descriptions, and now we need to categorize them as physical properties or chemical properties. So in the chat, I want you guys to put P for physical, C for chemical properties. Let's start with the first one. Neon is a colorless gas at room temperature. Is that a physical property or a chemical property? Excellent job. That's a physical property. Number two, apple slices turn brown when you expose them to air. Excellent. That's a chemical property. Phosphorus will ignite, in other words, catch on fire when you expose it to air. Great job. Chemical property. At room temperature, mercury is liquid. Is that physical or chemical? Great, a physical property. Lastly, propane gas is compressed to a liquid. So we're going from gas to liquid for placement in a small cylinder. What is that? That is a physical property because we're not changing the identity of propane. Propane just went from gas propane to liquid propane. So that's why it's a physical property. We're not changing the identity of the propane gas, okay? Any questions on the difference between physical and chemical properties? Let's now talk about changes that matter can undergo. So matter can have two types of changes. It can have physical changes or it can have chemical changes. And let's explore the difference between the two. Physical changes are going to occur when a substance has a change in state. And you can see in the bottom, the different states of matter that I discussed a few moments ago, going from solid to liquid to gas. So it is important that we actually define the terms that explore what describes the transition between solid to liquid, liquid to gas, solid to gas, okay? So these changes in state are the following. When I have a solid turning into a liquid, that is called melting. When I have a liquid going into gas, this is called evaporation. When a solid turns into a gas, that is called sublimation. Now, these changes are not only forward, they can also be reversed. So for example, if I have a liquid forming a solid, okay, that is called freezing. If I have a gas forming a liquid, that is called condensation. And if I have a gas forming a solid, that is called deposition. So understand that changes in physical shape, as long as they don't change the identity and the composition of a substance, are also physical changes. And as you can see here in the red words, every time there's a phase change, meaning going from solid to liquid or liquid to gas or solid to gas or vice versa, a phase change are always physical changes, as long as we're not changing the identity or composition of a substance. Now, we have a series of examples when it comes to chemical changes. And understand that the main thing about a chemical change is that a new substance is going to form, and this substance is going to have brand new composition and is going to have its own physical properties and its own chemical properties. Some examples of chemical changes include the formation of rust. In the case that we have here is iron rusting. When wood is burning, that's an example of a chemical change. Metabolism, so when we eat, all those changes that are happening to the biomolecules in order for us to derive energy, that's a chemical change. Cooking an egg, baking a cake, rotting banana, when you have vinegar and baking soda, fireworks exploding, all of those are examples of chemical changes. Now, in this week's lab, it is important to note that you guys understand that there's actually hints that tell you that a chemical change is happening. So there can be a change in properties. So as you guys can see here, when it comes to the change of properties, first, change in color can tell you that a chemical reaction has happened because the new compound made has a brand new color, okay? So for example, the Statue of Liberty, technically, if we think about it, is not green. The reason why it's green is because there is this substance that is called green patina. And this green patina, which is copper 2 oxide, it's coming from the copper, which is the material that the Statue of Liberty is made out of. When it reacts with oxygen, it creates this compound that is green. So that's why the Statue of Liberty, we see it as green because of copper reacting with oxygen and making a compound. Formation of bubbles can tell us if a reaction has happened. So understand that this formation of bubbles is not from boiling. The formation of bubbles is because the new substance made is a gas. And as it's trying to escape the liquid, that's why it's going to see, you guys are going to see some bubbling. Pay attention to bubbling when it comes to part B in the lab. Change in odor. So for example, when food is burning or food is rotten, you can actually smell that there's a change in smell. And it's because the new compounds that are made are going to have an odor or a change in odor compared to what you started with. The formation of a precipitate. So a precipitate in chemistry, this is going to be a solid substance formed in a chemical reaction. So you can see here in this beaker, and we look closely, that there is some liquid that is being poured onto the beaker, and this yellow substance is the precipitate. Okay, that is forming when we're combining the liquid that is being poured into the beaker. Now, we can also have changes in energy, indicate that there is a chemical reaction. So when things are warming up or cooling, or even the release of light, indicate that a chemical reaction has happened. So when it comes to the combustion reaction, which is part A of this week's lab, pay attention, okay, specifically to the release of light, which is very important that you notice for part A of this week's lab videos, okay? So let's just take a moment and as a group, again, utilizing P for physical change and C for chemical change, let's determine if the following are physical changes or chemical changes. Let's get started. Glass breaking, physical change or chemical change? Great job, physical change. Hammering wood together, physical or chemical? So rusting, a rusting bicycle. Great job. You guys got to handle this. This lab is going to run smooth for the rest of the semester. Melting butter. Physical or chemical? It's a physical, son. My son is participating with us. So it's physical.
I'm a young student, so I don't know that much. So
you'll be recorded. It's okay. So it's a physical change because look, we have those keywords that we learned from the phase changes, melting. So if we have those phase changes, okay, next, as an action of a substance, that's going to be a physical change. Separate sand from gravel. That's a physical change. Bleaching your hair. That's a chemical change. Good job, son. Yay. And good job to the students in the chat too. Frying an egg. No, frying an egg is a chemical change because the protein of the cooked. Exactly. So once you cooked it, that's done. Squeeze oranges for juice. Is that physical or chemical? Great job. That's a physical change. Yes. And then lastly, melting ice. No, that's not chemical. That's a physical change. Great job to the students in the chat. Okay. Any questions if you're given a description? Any questions? I'm trying to determine if something is a physical change or a chemical change. Excellent. Since there are no questions, this is the end of chapter 1. Let's move on to chapter 2 material, which in chapter 2, we are dealing with atoms and radioactivity. So the first thing that we're going to talk about is what are the components of an atom? So understand that an atom is going to be the smallest particle that we have of an element. So here, in the figure that we have in the slide, you can see that these are pieces of lithium. Lithium is made by lithium atoms. And when it comes to the components of the atoms, every single atom in the periodic table is going to have protons, neutrons, and electrons, okay? So taking that into account, we can see that specifically in the nucleus of an atom, we're going to have protons and neutrons. All of this is summarized in this table that I have on the slide. You can see the protons, the neutrons, and the electrons. What are the symbols for them? What is the charge for them? What is the mass of them? And their location in an atom. Now, why is it important that we know this? Well, because at the periodic table, which is something that we talked about in chapter 1, we can derive and find out what is the number of protons, neutrons, and electrons that a particular atom has. And this is how we find it. So when we look at the periodic table, we're going to have the following information. The periodic table gives us the symbol of an element, which you can see is here. It can give us the atomic number, and the atomic number is going to show up in, above the symbol. Here is right above it, or sometimes we can see it in a corner. Now, when it comes to those different components of an atom, the atomic number equals the number of protons. In chapter 3, we are going to learn about ions. So understand that for now, when it comes to atomic number, the number of protons and the number of electrons are going to be based on that atomic number, okay? We also have the atomic mass. And the atomic mass is what gives us the protons plus the neutrons. And that typically is below the symbol. So it is important to note that when it comes to the atomic mass, you need to round it to a whole number in order to do the calculation. So if I ask you guys for the following, How many protons do we have in potassium? Let's put it in the chat. How many protons in potassium? Great, 19. How many electrons? Great, also 19. Then what about the neutrons? So the neutron, if we isolate this, neutron equals atomic mass minus atomic number. Remember that it has to be a whole number, that atomic mass. So let's do that again. Great, 20. Okay. Now, when it comes to this, let's do some practice. Okay. So in the following table, we have just some information. I want you guys to take a moment and do the first row and the second row. I'll give you guys 2 minutes. Put a 1 in the chat if you're ready with the answers of the first and second row. Let me see how many people are done, or if we need to have more time. Put a 1 in the chat if you're already finished the work for first and second row. Okay, I'll give you guys 1 more minute. Let's get started with the answers for the first and second row. Okay. We are given in this table the atomic number. So just given the atomic number, we have a lot of things that we can fill in, okay? Because we can find out what is the element symbol. Let's put in the chat. What is element number 4? Great, brilliant, great job. Now, because we were given the atomic number, then we can find protons and electrons. So how many protons and electrons do we have? Separate them by a comma on the chat. Great job. 4 and 4. Now, when it comes to determining the mass number, okay? Because you were given the neutrons, mass number, okay, is going to be this plus this. So 4 plus 5, that's what you get the mass number. In parentheses, we can put the atomic mass, and the atomic mass is what it shows up in the periodic table. For beryllium, it's 9.012 AMU, which is the unit, which is atomic mass unit, okay? Any questions on number 1? On the first row. Let's move on to the second one. We know it is chlorine. So what is the symbol for chlorine, you guys? Great job. Cl. We have the atomic number given. So based on the atomic number, we know the number of protons and electrons, which is also 17. Okay? Now, when it comes to the mass number, understand that in this case, because we're not given the neutrons, we're going to base our mass number based on what we have in the periodic table. So since I know that my atomic mass is 35.45 AMU, well, my mass number is going to be 35, okay? Because it's just the whole number based on the atomic mass, at least for this case, which we are not given the neutrons. So to find the neutrons, then I'm going to take that 35 minus 17. So how many neutrons are in this chlorine? Great job. 18. Now, it is important to note that when it comes to elements, elements can have what are called isotopes. And when it comes to isotopes, these are atoms of the same element, but they have different atomic mass and mass number, okay? This table 4.7 is from a different textbook, okay? But this illustrates how we can have magnesium, okay, in 3 different flavors. To utilize an analogy, this is kind of like if you go shopping for vanilla ice cream, and when you are confronted in the ice cream aisle of your local supermarket, you can have vanilla ice cream that is homemade vanilla, French vanilla, vanilla bean ice cream, home style vanilla, Mexican vanilla. And all of these are going to have, again, the word vanilla, because everything is vanilla ice cream. It's just that it is just different variations on our vanilla ice cream. So isotopes are going to be variations on the same atom. It's just that they're going to have different atomic mass and mass number. When we write the name of these isotopes, as you can see, is given by the symbol and the mass number for that particular isotopes. So here we have magnesium 24, magnesium 25, and magnesium 26. Now, when it comes to isotopes, we also have what is called the percent abundance. And the percent abundance is what tells you, okay, if I take a sample of Earth and I'm looking for magnesium, the magnesium flavor that has the highest percent abundant is the most common. In your textbook, the way that it is explained is that the atomic mass that is closest to an isotope is going to be the most common magnesium. So right now, when we look at this, we can actually see that magnesium in the periodic table has an atomic mass of 24.31 AMU. So this, because the atomic mass on the periodic table is closest to specifically magnesium 24, then that suggests that that's the most abundant version of magnesium. But if we look at the given percent abundance, we can see that that is true. So I just wanted to mention that to you guys, okay? Now, on Thursday, we are going to specifically look into how to do isotopic notation. We are going to go back and explore isotopes in this table, and we're going to proceed to finish chapter 2 and move on to the first part of chapter 3, which is going to be the last concept that is coming in the exam next week. So thank you guys for coming. Have a good night.
Thank you.